तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. We are doing a course on basic electronics by the method of learning by doing. We saw in the previous lecture about different types of resistors, fixed resistors, variable resistors which are also called potentiometers, and some special type of resistors which are called, for example, LDR, light dependent resistor, whose resistance depends on the amount of light falling on it. And again we saw another different type of a resistor which is called thermistor, which really is a resistor whose value depends on the amount of heat or temperature. Next we also saw the basic law of physics of electronics, which is basically Ohm's law, which says that the current in a given conductor is proportional to the voltage applied across its terminals. This is one of the very fundamental laws of electricity and electronics, and if one knows this very well, and then you would be in a position to understand the working principle of several circuits. Then we also saw about what is an ideal voltage source. Voltage source will always have an internal resistance which will normally be very small, but still it exists, and therefore when you draw current from a voltage source, you would always find that some voltage is dropped across the internal resistance, and thereby the exact voltage available for you at the terminals of the voltage source will be less than what you would otherwise expect. Ideal voltage sources are characterized by zero resistance. So these are very important concepts in the whole idea of electronics, and therefore we also saw the actual practical experiments relating to all these things. We saw the LDR, we saw the thermistor, we saw the ideal the voltage source and things like that. Today in this lecture we will look at the combination of resistors, how resistors can be combined to obtain different values, as well as how to divide a given voltage source to any required magnitude by using couple of resistors, which is basically called a potential divider because it divides a potential. Then we will also see the next type of components that we would be making use of in electronics, namely capacitors. And lastly, we will also see some basic ideas about the coils, the inductances as we call it, and transformers, which also form a very important part of learning electronics. Now when we have only one particular value of resistor, for example, and you want to have a larger value of resistance, for example, then what do? I have, for example, I will give you a typical number. If I have 1000 ohms with me, quite a large number of them, but I want to obtain a 3000 ohm resistor, I do not have 3000 ohm resistors, I must be able to obtain 3000 ohms resistor with the available 1000 ohm resistors. How do I combine them? Is there a way I can combine the different resistors to obtain a larger value of resistance, or is there a way to combine the different resistors to obtain a value which is smaller than the value that I have? So, these will have to be discussed, and the one way, there are two different ways of combining the resistors in a given situation. They are called series combination and parallel combination. So, you may be, some of you may be familiar with the series combination and the parallel combination. You come across this type of concepts in several other similar situations also. For example, I would draw your attention to the circuit that I have drawn. You can see that there is a very simple circuit which makes use of a voltage source which is shown in the form of a battery with a plus and minus sign, and the V, that is the magnitude of the voltage, and that is connected to two resistors which are R1 and R2, as you can see on the screen. So, when the R1 and R2 are connected one after another in this way, it is called a series connection. The series connection is characterized by a same current flowing throughout the circuit. You can see the current, if it starts from the plus terminal of the voltage source, it goes along this wire and into this resistor and comes out of this R1 and goes again into the next resistor R2 and comes out and completes the circuit. So, if a current is the same going through all the resistors connected in a given circuit, then that combination is called series combination. So, series combination is characterized by a same current flowing through all the resistors forming the combination. So, in that case, what will be the total resistance in the circuit? It is very easy, because the total resistance is just the sum of the individual resistors. So, in this example that I showed you, the total resistance capital R, for example, is equal to R1 plus R2, because we have used only two resistors. The combination is the sum of the two resistors R1 and R2. Okay, so the calculating the values of two or more resistors in series is very simple, because you just have to add them all together. The second point which I already mentioned to you is that in this type of connection, the same current flows through all the resistors. This is a second important point. The third point which we should always remember in series connection is that in this type of connection, the total resistance will always be greater than any one of the individual resistors, because the total resistor is obtained by summing all the resistors, and therefore, obviously any resistor will be in value less than the total resistance, or in other words, the total resistance will always be larger than any of the individual resistors. This is one of the very important ideas in the series connection. Now, you should not think, because I showed a circuit with only two resistors R1 and R2, you should not conclude that we can only have two resistors in combination. As a matter of fact, you can add any number of resistors in series, R1, R2, R3, etc., and the total resistance will always be given by R1 plus R2 plus R3 plus etc., as many resistors as you have connected. So, it is always possible by having a set of resistors, same value resistor. For example, I gave you the number 1000 ohms. So, if I have only 1000 ohms, it is always possible that you can combine them and get a value of resistor which is larger than any of the value of the resistors that you have. For example, 1000 ohm. You can easily form, for example, 3000 ohms resistor by combining three 1000 resistors in series. Like that, you can have any value larger than the value that you have. Now, I just mentioned how this happens, but let me just try to explain to you how this could be understood in a very simple way. If you see on the screen, the total applied voltage is actually divided by the two resistors R1 and R2. How is that? We can have a look at that. All that we need to know is the simple law of Ohms. So, now you can see what is the current in the circuit that I showed you. I have given that circuit again once again in this frame. You can see there is a battery, the R1 and R2 connected in series. So, if I want to measure the current in the circuit, you know by Ohm's law, current is equal to voltage by total resistance. The voltage here is V and the resistance here is a combination of the two resistors R1 and R2, and therefore, current I is given by V by R1 plus R2. I am sure everyone knows this. Now, if I know the current, then it is simple matter to obtain what will be the voltage that is developed across each one of the two resistors that I have in the circuit. For example, if I want to find out what is the voltage across R1, you can immediately see that voltage, if I call it as V1, V1 is by Ohm's law given by current into resistance. Current is I, resistance is R1, and therefore, instead of I write the V by R1 plus R2, which we know as the current in the circuit. Therefore, V1, the voltage across resistance R1, is given by V by R1 plus R2 into R1, corresponding to I into R1. Similarly, the voltage across V2, the resistance across R2. So, the voltage across the resistance R2 is given by I into R2, where I is again given by V by R1 plus R2, because it is the same current which is flowing through both the resistors, and therefore, V2 is given by V by R1 plus R2 times R2, and therefore, we have seen there are two voltages V1 and V2 developed across the two resistors, and what will be V, the total voltage? That will be equal to V1 plus V2, as you all know. And if I now put the expressions that I got for V1 and V2, namely V by R1 plus R2 into R1 plus V by R1 plus R2 into R2 for the second resistor, you can see that V by R1 plus R2 is a common which I can take out. Then you would find R1 plus R2 will be the one which will be available, and that R1 plus R2 will cancel with the R1 plus R2 at the denominator, and so I will again get back V, the total voltage. So, what do we understand from this? We understand that when I connect two resistors in series, they divide the voltage, the total voltage V. So, if I, in this case, the total voltage is divided as V1 and V2, where V1 you can see is proportional to R1 because it is I into R1, and V2 is proportional to R2 because it is again I into R2, where I is a constant which flows through both the resistors, and therefore, you can see the series resistors divide voltage. That is what we want to understand from this. Now, I will try to explain to you with a typical example with numbers. Let us assume that we have a voltage source V of 6 volts, and the two resistors, let them be 1000 ohms each, or 1 K, as I shown here, 1 K. Then the total current in the circuit, you know, is given by voltage divided by total resistance. The voltage here is 6 volts, and the total resistance, because I have used two resistors in series, the total resistance is 2000 ohms or 2 K. So, 6 volts by 2 K gives me 3 milliamperes. The K in the denominator will go in the numerator as 10 power minus 3, and therefore, 6 by 2 is 3, 3 into 10 power minus 3 ampere, and 10 power minus 3 ampere is known as milliamperes. So, the current in the circuit with one 6 volt supply and two 1000 ohm resistors connected in series will be 3 milliamperes. Now, if we know the current, then immediately we can obtain what is the voltage developed across each of the two resistors. All that I have to do is multiply by the current by the corresponding resistance. The current is 3 milliamperes and the resistance is 1 K. So, I should multiply 3 into 10 power minus 3 ampere by 1000, and 1000 is nothing but 1 into 10 to power 3, and therefore you can see the 10 power 3 and the 10 power minus 3 will cancel, and I will left with 1 into 3, which is 3 volts. So the voltage across the resistor R1, which is 1000 ohm, is 3 volts. By the same reasoning, you can immediately guess the resistance across the second resistance, which is also 1000 ohms, will be another 3 volts. So the total voltage therefore will be 3 plus 3, 6 volts, which is the voltage of the power supply. And therefore you can see the total voltage of the power supply, which is in this case 6 volts, is divided equally by the two equal resistors 1000 ohms each. Now if I do not have equal resistance, for example one resistance is 1000 ohms and the other resistance is 2000 ohms, then you would find the total voltage will also be dividing proportional to the resistor. That means across the 1000 ohms there will be less voltage, across the 2000 ohms there will be more voltage. In this case, because it is 2 plus 1, 3000 ohms I have in the circuit, if I have 6 volts, 6 volts by 3000 ohms gives me 2 milliamperes, and that means the total current in the circuit is 2 milliamperes in this case, and the voltage across 1K therefore will be 2 milliamperes into 1K, which is 2 volts, and that across the second resistor 2K is 2K into 2 milliamperes, which is equal to 4 volts, as you can see. And therefore series resistors have same current flowing through them and they divide voltage. These are the two important points that we should always keep in mind. Thus I have summarized here, the series connection is characterized by 1, the same current flows through all the resistors connected in series. 2, the resultant resistance is the sum of all the resistance connected in series, and lastly series resistor divide the total applied voltage proportional to their magnitude. Once having learned about the series combination, let us move on to the next, which is connecting them in parallel. When you can immediately imagine when I connect them in parallel, that means you can see the circuit that I have shown on the screen. You can see that both the resistors are connected across the voltage source. That means if I have this I call as the head, this I call as the tail of the resistor, you can see the head of one resistor and the head of the other resistor are connected together, and the tail of one resistor and the tail of the other resistor are connected together, and both of them are connected to the power supply in this direction. So this is characterized by the parallel combination, and immediately you can imagine what is happening to the current. The current which comes from the voltage source will have to divide here because there is a junction here, and so the current divides and you get different currents flowing through the two different resistors R1 and R2, and then they come again together, add together and come out as a total current I. So immediate thing that you can see in a parallel combination is that the current divides, but something else is constant. Just as in a series resistor combination the current was a constant, here something else should be a constant. What is constant in a parallel combination? You can immediately see the voltage applied across each of the resistor is a constant. You can see the same voltage E or V is applied across this resistor R1, and it is also applied in this resistor R2. Therefore parallel combinations are characterized by same voltage appearing across all the resistors, and secondly the current divides in a parallel resistor. So this is important. How do I obtain the total resistance or the combination resistance in the case of resistors which are connected in parallel? So I have given the formula on the screen now. If two resistors are equal, then you can imagine because they are equal they will have equal currents flowing through them, and therefore the when the current divides you would also see the resistance will also be half of the full value that you can think of. That is, if R total in general the formula is given by 1 by R total is equal to 1 by R1 plus 1 by R2 plus etc., depending upon how many resistors you connect in parallel. So, if I have this complicated relationship in terms of reciprocal can be looked at easily by taking R total is equal to R1 R2 divided by R1 plus R2 in the case of two resistors R1 and R2 connected in parallel. So, the formula for total resistance of two resistors connected in parallel is very simple. You find the product of the resistors divided by the sum of the resistors will give you the resultant of combination of two resistors connected in parallel. So, let us again take a numerical example as before. Let us assume that we do have the same 6 volts power supply, and for simplicity again we assume the two resistors which are connected in parallel are 1000 or 1K each. So, the current through the resistor will be, because you can now see each resistor is connected to 6 volt supply independently in parallel, and therefore 6 volts by 1000 ohms or 1K is the current corresponding to one resistor, and that is equal to 6 milliamperes as we have seen before. So, 6 milliamperes of current flows through R1, and again 6 milliamperes of current flow through R2, and therefore you can see the original current which divided into the two resistors will have to be 6 plus 6 or 12 milliamperes. Now, what resistance when I connect across a 6 volts power supply will give me 12 milliamperes of current is a very simple problem. Immediately you can imagine, only if I have half K resistor, that is 500 ohms, which is equal to 0.5 K. If I connect, then you can see 6 volts by 0.5 is 12, and therefore the total current will be 12 milliamperes, and that means what is the effective resistance of the two resistors 1000 ohms each I connected in parallel, and the effective resistance as you can see is 500 ohms or 0.5 K. So, when I connect two resistors in parallel, the effective resistance becomes less, in this case half, because I have used two equal resistors. If I have more than two resistors connected in parallel, you can imagine that the effective resistance will still be lower. For example, if I use three equal resistors in combination, in parallel combination, the effective resistance will be 1/3. So, 1K, 1K and 1K connected in parallel, the effective resistance will be 1/3 times 1000 ohms or about 330 ohms. Here I have shown when I connect the two 1K resistors, I can also use the formula to obtain the effective resistance. R total is given by, I already mentioned to you, R1 into R2 divided by R1 plus R2. In the equal resistance case, I have 1000 ohms into 1000 ohms, or here 1K, I have done it everything in kilo ohms. So, 1 into 1 divided by 1 plus 1 kilo ohms, and that is nothing but 1/2 kilo ohms or 0.5 kilo ohm. So, if I, instead of using equal resistors for R1 and R2, if I use different resistors, R1 is different from R2, then you can immediately imagine the two currents that the single current divides as I connect them in parallel will also be different. In the previous case, the two currents were equal because I used equal resistors. So, different resistors divide current differently, and you know how it will divide. If the resistance is more, the current will be less. They have inverse proportion. If the resistance is less, the current will be more. So, if I have two resistors R1 and R2, R1 is larger than R2, then you can imagine the current through R1 will be less compared to the current through R2. But still the total current will be the sum of these two currents, which will be the one which will coming out of the power supply. Now, summarize the various important points that we should remember when we have resistors connected in parallel. The same voltage exists across all the resistors connected in parallel. That is one important point that you have seen that already. And the reciprocal of the resultant resistor is the sum of the reciprocals of all the resistors individually taken in the case of the parallel resistor. And the last point is parallel resistors divide the total current in an inverse proportion to their magnitude. Larger resistor provides less current, smaller resistor divide larger current. Another very important point with reference to resistors when connected in parallel is that the effective resistance of such a parallel combination will always be smaller than the smallest of the resistor that you have used in the combination. For example, if I use 1K and 1K the combination, then the parallel combination we have seen already is 0.5K, it divides by 2 because I have used 2 equal resistors. Instead, if I for example use 1K and 10K, that is 1000 ohms and 10,000 ohms. If I use 1K and 10K, then the resultant is 10 into 1 by 10 plus 1, that means 10 by 11, which is equal to 0.9K approximately, and that means smaller than the smallest of the 2 resistors that I used in this circuit, which is in this case 1K. So 0.9 is less than 1K. If I use 1K and 100K in parallel combination, then the resultant you can immediately find out will be 1 into 100 divided by 1 plus 100, and that means 100 divided by 101, and the value is about 0.99K. So you can see if the 2 resistors are equal, the effective resistance is half. If the 2 resistors are differing by a large value, then you find it is much closer to the smaller of the 2, much closer to the 1000 ohms. When I use 1000 and 10,000, it is 0.9. When I use 1000 and 100,000, it is 0.99, and therefore as I increase one of the value of the resistors to the larger and larger value, you would find the effective resistance will be almost related to the smaller of the resistors. Okay, this parallel combination, series combination we have understood. Now we will be in a position to apply these combinations in different situations. One immediate application that you can think of with series resistors is the concept that I have already mentioned to you, that series resistors divide voltage. So because they divide voltage, if I have a power supply which is, let us say, 10 volts output, but I find I have a circuit which I constructed which requires only 5 volts, then what do? I do not have any other power supply. I have only a 10 volt power supply, and I require to be used in a situation where I require only 5 volts. So what do? Yes, the idea is very simple. You can use 2 resistors in series. You connect the 2 resistors in series to the 10 volts and make sure the 2 resistors are equal. Then you know equal resistors in connected in series divide the voltage equally, and therefore the 10 volts will be divided equally. That means I will get 5 volts and 5 volts across each of the resistor. So if I connect the output of one of the resistors, the voltage developed across one of the resistors to my circuit, I will get 5 volts required for my circuit. But there is one important point which you should remember. You can always divide the voltages proportional to the resistance, as I already mentioned to you, and therefore depending upon whether you want 5 volts or 6 volts or 10 volts, you can divide the resistors, suitably select them, and then obtain any division that you require. But unfortunately, what value of resistors you will choose for making a potential divider? Because I said only that to get half of the total voltage I require 2 equal resistors. The 2 equal resistors could be 100 ohms each, could be 1000 ohms each, could be 100,000 ohms each. Which is the best one to choose? All these combinations, whether I use 100 ohms and 100 ohms or 1000 kilo ohms and 1000 kilo ohms, whatever I use, as long as I use 2 equal resistors, the voltage will be divided equally. So in all the cases, the division of voltage will be the same, but something else will happen that you should remember. You are dividing the voltage because you want to apply a smaller voltage to a different circuit, and that circuit, for functioning, it requires a current. That means you must have enough current, minimum current required to operate the circuit should be available from your power supply. So, if I put, I just want to show you on the screen, you have got a voltage supply V in now divided by 2 resistors R1 and R2 and apply the voltage across R2 as V out. I take it for connecting to the any other device. The equation that I have shown here is V output is V in multiplied by R2 divided by R1 plus R2, which is a very simple relationship which you can obtain from Ohm's law. But the point I want to tell you is, when I want to have a load or some circuit connected across the output of R2, you would find that the current for this circuit will have to come from your main power supply, which is V in, through the resistor R1 also. And therefore, if R1 is 100,000 ohms, then you can imagine the current which will come to the output circuit will be limited by the R1 resistor which is coming in series. And therefore, you would find if I use very large resistors here, I will not be able to get enough current for applying to different circuits that I have at the output, and therefore, one has to choose reasonably small values of resistors for R1 and R2, especially when you want potential divider. But how small? Can I put 10 ohms and 10 ohms and divide the voltage? Again it will divide equally, but because it is 10 ohms I can get very large current, therefore there is no problem. Yes, you can certainly get very larger current using 10 ohm 10 ohm combination, but you should always remember 10 ohm will make a large current to continuously flow through the circuit, and therefore there will be a large current flowing through these two 10 ohm resistors. That means there is a power loss in terms of the power rating of the resistors R1 R2. There will be some heat loss in these resistors which will be unnecessary, and therefore one has to have some via media in between. You should not use too large values, you should not use too small values, and therefore you will use reasonably small values, like maybe 1000 ohms is a reasonably good value that you can think of. In this screen I wanted to show you the relationship, how do I obtain the output voltage as R1 by R1 plus R2 into V in. I is V in by R1 plus R2, that we already know. The total current is total voltage divided by total resistance, and since this current flows through R2, in this case I multiply by I into R2, and that is V in R1 V in divided by R1 plus R2 into R2, which I have rewritten as V output is R2 by R1 plus R2 into V in. So this is the concept of the potential divider, and I have given some examples. If the two resistors are equal, then you can immediately see that V output will be V in by 2, that we have already seen. Equal resistors divide voltage equally. I also mentioned to you in the potential divider the current flows through R1, and therefore one has to choose carefully the value of R1. We can also have the two resistors replaced by a variable resistor if necessary, that is also possible. And then the last point which is very important in potential divider is with reference to the power rating, power dissipation. We should always use resistors which are not too small, resistors which are too large, but something in between, maybe about 1000 2000 ohms will be reasonable value of resistors to be used in parallel combination, series combination for obtaining potential dividers. So in principle I will just give one or two simple ideas. 4 identical quarter watt resistors, 0.25 watt resistors can be wired in parallel to give a resistor of 1/4 the value in ohms, but 4 times the power rating, because the current will be 4 times, whereas the resistance value will be 1/4 because you have connected them in parallel. This is most useful when we require higher power rating resistors, but we cannot buy them immediately by going over to the shop. So you can use these simple techniques for obtaining larger power rating for your resistors. And we have already discussed power is proportional to voltage into current, and therefore we must make sure when we connect resistors in parallel that the parallel resistors require larger power rating, and therefore carefully choose the combinations so that there is no problem with reference to power rating. If you use a resistor which has got a lower power rating, then the resistor will go bad when you connect them in series due to the heat dissipated, or it could also start a fire. Next, this is about the voltages combinations in series and parallel. Now, I will quickly go over to the experiment and show you the different ways of connecting the resistors in parallel and series, and then we will let us try the experiment now. Here I have a power supply, and the two wires from the power supply are connected to a breadboard, which we have already seen, and you can see I have connected two resistors here. Each one of them is 1000 ohms. Some of you are familiar with the color code, which I already mentioned. You can see that it is brown, black, red and gold. Here again brown, black, red, gold. Therefore, these are 1K resistors connected, and the power supply comes here, and I have connected a current meter, milliammeter, between one point and the power supply and the resistor series combination. So, I connected this meter in series in the gap, and the two resistors are also connected in series, and the negative power supply goes back to the power supply. So, the two resistors are connected in series. I have about approximately 6 volts or so, 5.9 volts. So, when I have 5.9 volts, two resistors equal to 2K, 6 by 2K is around 3 milliamperes. So, you can see this bigger division is 5 milliampere. So, it is nearly 6 divisions, that corresponds to 3 milliamperes of current. So, you can see again it is following Ohm's law, and that two resistors have got the same current flowing through them, which is given in this case as 3 volts. Now, I have a voltmeter which I have connected corresponding to the voltage, and it is now measuring DC volts between these two terminals, and now I will use this to measure the voltage across the one of the resistors. For example, I connect the bottom to the ground, I take the other wire and connect it to the midpoint. If it is connected to the midpoint, then it is measuring the voltage across the lower resistance R2, and you can see the voltage is 2.9 something, which corresponds to really 3 volts approximately. And therefore, when I connect 6 volts to two equal resistors, the voltage across one of the resistor is found to be 3 volts. Similarly, you can see the voltage across the other resistor will also be equal to 3 volts. Therefore, the total 6 volts is divided among the two resistors connected in series, and therefore, the concept that same current flows through both the resistors and series resistors divide voltage is very well understood by doing this. Now, what about the combination? I have used two resistors, which is in this case 1000 each, and therefore, the total resistance, as you know, is 1000 plus 1000, 2000 ohms, and therefore, what I have now done is I have connected here another resistor whose value is nearly 2000. It has got, by you can see the color code, three red strips, red, 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 which is equal to 2.2 K or 2200 ohms, very close to 2000. Now, I am connecting that in the circuit, and let us see what will be the current. Now, you can see the current is the same as what before that you measured when I had two different resistors, each of 1000 ohms, now replaced by 2200 ohms, and you can see the current is almost the same as the previous case. That means two 1000 ohms connected in series is equal to one 2200 ohms, equal 2000 nearly ohms resistor, and therefore, the combination of resistors when I connect them in series is just obtained by summing all the resistors. That is what I wanted to show you. Now, let me go on to the parallel combination. You can see here I have two resistors, again they are 1000 ohms 1K resistors. I have connected them together at the bottom, and the top one I will connect to the power supply quickly. So, I take the power supply, connect it at the top point, and I want to measure the current flowing through each of the resistors. Therefore, one end of the current meter I connect to the power supply, the other end I connect to one of the resistors. Similarly, I will take the other ammeter also, milliammeter, to the second resistor. Yes, now I will connect the negative of the power supply. I hope you can see that now. You can see this is nearly 6 volts, 6 milliamperes. This also is 6 milliamperes. Therefore, I have 6 milliamps through one of the resistor, 6 milliampere through the other resistor. The total resistance will be 12 milliampere, which I can actually monitor using this if necessary. So, you can see, because I have 6 volts appearing across both the 1000 resistor, both the resistors will generate 6 milliamperes independently, and the total current will be the sum of the two currents. Therefore, a parallel combination divide current, and they have the same voltage, 6 volts across them. 6 volts divided by 1000 is 6 milliamperes, here also is 6 milliamperes. So, we can see that parallel resistors divide current and they have the same voltage. That is what I just wanted to show it to you. So, we have seen an actual demonstration of the series and parallel combinations of resistors. Now, we will move on to the next component, which is capacitors. So, what is a capacitor? A capacitor is basically a device which has got in general two parallel plates separated by an insulator or a dielectric. It is used for storing electrical energy, and capacitors is characterized by very large resistance to DC or the direct current and smaller resistance for alternating current. So, I have shown a construction of a typical parallel plate capacitor, which is the most popular one. You can see there is one plate here connected to a wire, and there is another plate here connected to another wire, and you have in between a dielectric, which is basically air or any other insulator. So, the value of capacitance, these things you would have studied in our earlier classes. The value of capacitance is given by epsilon 0, epsilon r A by D, where A is the area of the capacitor, D is the distance of separation between the two plates, and epsilon 0 and epsilon r are constants. Epsilon 0 is called the permittivity of free space, and epsilon r is the dielectric constant or the relative permittivity of the medium. So, you can see the capacitance of a capacitor is proportional to area, because it comes in the numerator. It is inversely proportional to the spacing. That means, smaller the distance between the plates, larger will be the capacitance, and it also depends on the dielectric constant or the nature of the medium that I have in between the two parallel plates. So, when a DC voltage is applied to a capacitor, the capacitor gets charged. The charges start flowing into the capacitor, they stay on the plates, and thereby they get fully charged. Now, just as the charges get accumulated on the plates, there will be a current flowing when I immediately connect a capacitor to a battery. But then this current will slowly come to 0 as the charges accumulate on the plate, and therefore, finally, when it is fully charged, the current flowing through the capacitor will be 0. There will not be any current at all in the circuit. So, if we measure the resistance of a capacitor, you can imagine resistance is in this case will have to be very large or infinity, because you have two plates, there is no connection between them, there is no electrical connection, and apart from that you have introduced a dielectric, either air or any other glass or any mica, things like that, and therefore it will show infinite resistance. Hence, obviously the capacitors will block DC, direct current. However, when a AC voltage or current is applied, the capacitor will offer some reactance, as it is called. It is not resistance, it is reactance, because it is only responding to time varying signals of voltage and current, therefore it is called reactance. The value of Xc, which is the reactance offered by a capacitance, is given by 1 by omega c, where omega is the frequency component, omega is the angular frequency, which is given by 2 pi times the f, the frequency of the AC, and c is the capacitance in farads. Usually the unit of capacitance is farad. Farad is a very large value of capacitance, and therefore only some super capacitors will have capacitance in the range of farad. The normal value of capacitance is measured in microfarad, which corresponds to 10 power minus 3 farad, or nanofarad corresponding to 10 power minus 9 farad, and sometimes even picofarad, which corresponds to 10 power minus 12 farad. These are the scales that normally we use, and we also use, similar to the resistors, a 3-digit code which indicates the value of the capacitor, or sometimes they put in terms of some numbers on the capacitors if it is possible. Just as resistors, capacitors can also be combined, and you can combine them again in a similar fashion in series, as I have shown here. For example, C1 and C2 are connected in series, and if I connect them in series, the formula that you use is much more closer to the parallel combination of resistors, that is 1 by C total is equal to 1 by C1 plus 1 by C2, and this is the formula we will use when you connect capacitors in series. And if I have only 2 capacitors, then the total capacitor or the resultant capacitors is given by C1 C2 divided by C1 plus C2, just as we had a similar situation with reference to parallel resistors. If you connect the capacitors in parallel, then you can see they add, as you are doing in the case of series resistor. So C total in the case of capacitors connected in parallel is nothing but C1 plus C2. So you should observe the difference between the combinations of capacitors and the combinations of resistors. Okay, just as resistors are characterized by a value and the power rating, what wattage it can withstand, similarly capacitors are characterized by the capacitance in terms of farads or microfarads or whatever, and also another important characteristics, which is the voltage, the maximum voltage that I can apply to the capacitor without breaking down the capacitor. If I keep on applying voltage, you would find if I exceed a threshold, then the dielectric will break down, making very large current to flow through that, and that is what is called breakdown voltage. So breakdown voltage is one other important characteristic of the capacitors, and therefore when I buy a capacitor, I should specify what is the operating voltage. If I am going to operate the capacitors to 6 volts, 12 volts, etc., then I can go for some 25 volts capacitors or 50 volts capacitors, as the case may be. But if I am going to operate the capacitors in regions where the voltages could be as high as 1000 volts or 2000 volts, then I should buy capacitors with very large breakdown voltages of the order of 5K or 10 kV and things like that. Then you also have different types of capacitors. The different types of capacitors come about because of the different types of dielectric material that you introduce between the 2 metal plates. So in the case of electrolytic capacitors, which are widely used in different situations in circuits, you would find the electrolyte is used as a dielectric. The dielectric in this case is an electrolyte, and so usually aluminum will be used as an electrode, and the electrolyte will have some polarity consciousness. Now it has to be very carefully connected in circuit, because they will be marked with a very specific direction, plus and minus for the leads. If you interchange them, it will lead to some difficulty, because the current will flow in the opposite direction, and therefore it will evolve some gases, and finally it may also explode sometimes. So one has to be very careful when we use capacitors in the lab. You should make sure, especially electrolytic capacitors, you should look for the plus and minus seen in the capacitors and connect it properly in the circuit with the right polarity. Then you may be asking why we are using a polarized capacitor when you said capacitors will conduct only AC. There is no DC here. Only in DC we have plus and minus sign shown. Why in an electrolytic capacitor you still call it capacitors, and then there must be, you are marking plus and minus on the top. So, the reason here is the AC that you use in the case of electrolytic capacitors will be the varying DC. So, you will have an average DC over which there will be a variation or an alternating voltage, and therefore, it is something like, for example, the ripple voltage in the case of a power supply, things like that. So, electrolytic capacitors are always used under DC conditions, but varying DC conditions, and therefore there is no harm. Still, they will only take care of the alternating voltage that is being applied. So, I have here some examples of electrolytic capacitors, and the values also are shown. You can see this first one is 1 microfarad, the last one is 1000 microfarad, and you can see the 50 volts of operation. So, all of them are characterized by a value of capacitance in microfarads and a value of voltage, which is the maximum voltage I can use it under different conditions. So, these are electrolytic capacitors, and I will go on to show you the other type of capacitors. For example, tantalum capacitors. Tantalum capacitors are also electrolytic capacitors. They use a material called tantalum for the electrodes, and they are superior compared to the normal electrolytic capacitors. They have very high stability, and they are used mostly in analog signal systems. Then I have given some examples of the tantalum capacitors: 0.33 microfarad, 0.47 microfarad, and 10 microfarad. You can see the sizes also are different depending upon the value, but the voltage in all the cases is 35 volts, which is the maximum voltage. Then you have other type, which is called ceramic capacitors, and they have a titanium barium oxide, which is used as a dielectric internally, and they are used usually for high frequency applications. Then you also have, these are some of the ceramic capacitors. One is 1000 picofarad, and the symbol they use, for example, you can see here, I hope, is 103, which corresponds to 10, the first two digit 10 into 3 corresponds to 10 power 3 picofarads, which is equivalent to 0.01 microfarad. So, then you also have polystyrene film capacitors, where the polystyrene film is used as the dielectric, and this type of capacitor are also used in different applications. I have given some examples of the polystyrene capacitors here. The light brown color is due to the copper being used as the electrode material. Then you have electric double layer capacitors, which is called a supercapacitor, and the value of the capacitance is 0.47 farad. You should remember, it is not microfarad, it is 0.47 farad. That means it is a very large value of capacitance. I will show you the picture. You can see here, this is a very large capacitor which has to be very carefully handled. Then you also have polyester film capacitors. Again, you have polyester used as the dielectric. They are very cheap, they have very reasonable tolerance of within plus or minus 5% or plus or minus 10%, and these are the polystyrene capacitors that I mentioned to you in the screen: 0.01 microfarad, 0.1 microfarad, 0.22 microfarad, etc. Then polypropylene capacitors, again this is another dielectric they use. And then you have mica capacitors, where mica is used as the dielectric material, and it is used for high frequency and resonance circuits. They have very good insulation. And you have dipped mica capacitors are the last thing: 47 picofarad, 220 picofarad, and 1000 picofarad are available. So, you also have metallized polymer film capacitors. They are much more rugged, they have no polarity, and these are, the figure shows such metallized capacitors. You also have, just as you have variable resistors, you also have variable capacitors, which are used for adjusting the frequency in a tuned circuit and things like that. You can use a special screwdriver and vary. What is being done here is the area of contact, the area between the two plates will be changed, thereby the capacitance will be changed. I have shown here pictures of variable capacitors. You can see there is a you can use a screwdriver here and move this on top, which will vary the capacitance from 3 pf to 27 pf, etc. I have shown some more variable capacitors here. This is a ganged capacitor. In the olden days radios, we make use of these things. This is also a variable capacitor with a polyester film used as a dielectric. The variation is about 12 picofarad to 150 picofarad, very large values you can change. Finally, we will come on to the coils and inductances. These are also very useful in electronic circuit. You have a copper wire wound over a former, which becomes an inductance, and the inductance is normally measured in units of Henry. And the coils are also very useful in many circuits, because you want to have resonance circuits and things like that. The symbol is L for the inductance and the unit is Henry. Usually you use microhenries and millihenries etc. as units, and the characteristics of the coil is that when current attempts to change, then there is a reactance. So whenever current changes, there is in the case of capacitor, whenever voltage changes, there is a reactance. Here, whenever the current changes, there is a reactance, and that is due to the electromagnetic effect that we know of, Lenz's law. Now I have shown some simple examples here where this is a transformer where you have a primary and a secondary. So when I apply a AC voltage to the primary, due to the mutual inductance between the primary and secondary, there is a voltage also induced in the secondary, and therefore they can be used to get smaller voltage, AC voltage from a larger voltage, or the larger voltage from a smaller voltage, etc. So transformers are very useful. Similarly, coils are also used in electromagnetic relays to operate secondary circuits. I have shown a simple circuit here. When current flows through this, the magnetic field will make the switch close, and therefore you can switch on an independent circuit by using these relays. We will later on see some demonstrations of such things, and coils are also used in resonance circuits. I already mentioned to you many of the circuits, and this is a parallel resonance capacitance and inductance connected in parallel, and the frequency of this parallel combination is 1/2 pi root LC, where L is the inductance and C is the capacitance. And this is something like a simple pendulum or a mechanical oscillating system. Here it is an electrical oscillating system. The capacitor gets charged and it passes a current through the L, it produces an opposing back EMF that again charges the capacitor, and so this goes on and on till all the energy is lost. And therefore this is a graph corresponding to the resonance circuit which is shown, and this is another circuit which is a series resonance here, and I have given some photographs of various different types of inductances that we normally use in the electronic circuits. These two are actually transformers, high frequency transformers or intermediate frequency transformers. So you can adjust the value of the inductance by using screwdriver and vary the inductance value. Finally, let me just summarize the various ideas that we looked at today. We studied about resistors in combination, series and parallel, and then we also saw how resistance can be connected in series to divide voltages as potential dividers, and we also saw a demonstration of this series parallel combination, and then we looked at different types of capacitors corresponding to different type of dielectric material that we use in them, and how capacitors can be used in different circuits. And then finally we saw about the inductance or the coils and the transformers. Transforms the voltage from one level to another level, and they are very useful in high frequency as well as low frequency application. For example, every power supply that you think of in every instrument, electronic instrument, you would find there will be a transformer which is responsible for bringing down the 220 volts mains to some smaller value, which can later be converted into direct current or whatever. So transformers are very, very useful in power supply circuits. Capacitors and resistors are very useful in several electronic circuits, and in the next lecture we will try to look at a new type of device which is p-n junction diode, and special type of diodes and applications of diodes we will see. Thank you.